Hi everyone, this is Maverick Pua, the chemistry guru. Now in this video, we want to discuss the different types of stereoisomerism. Now stereoisomers, they have the same molecular formula, they have the same structural formula, so therefore they are very similar in terms of physical and chemical properties, but because of the different arrangement of their atoms in space, they are actually different compounds. So we can see stereoisomers as a pair of identical twins. They might have the same height and weight, they look exactly the same, they might even behave similarly, they even usually have similar names, right, for identical twins, but of course they're different persons. So we can use this analogy to compare stereoisomers. They may look exactly the same, they have very similar physical and chemical properties, they can even have very similar names, but in fact they're different compounds. Now in A-level chemistry syllabus, we have two different types of stereoisomerism, Cis-Trans Isomerism and Optical Isomerism. Now the first type of stereoisomerism is Cis-Trans Isomerism or geometric isomerism. Now this usually occurs for alkenes, and the criteria for alkenes to have Cis-Trans Isomerism is each of the carbon of the alkene must be bonded to two different groups. So we have in this example here, build 2-in. You notice if we focus on the alkene, maybe if I box up this alkene, so it makes it easier for us to focus on the two carbons. You notice this carbon on the left hand side, it is attached to two different groups, a methyl group and a hydrogen. Usually in terms of comparison, in order for us to determine which is a cis isomer and which is the trans isomer, we would look out for the bigger group in terms of MR. So methyl group versus hydrogen, methyl is bigger in terms of size, so I can highlight this. So this will be the bulky group, or this will be the big group that is attached to this carbon. Now, how about the other carbon? This other carbon inside this alkene, it is also bonded to two different groups, also to a methyl group and a hydrogen. So same thing, the group which is bigger in terms of size, I will circle this group. Now, if I have an alkene where each of this carbon is attached to two different groups, then in principle, this alkene can exhibit cis-trans isomerism. Now, in order for us to draw out the cis isomer and the trans isomer, what we have to do is we have to draw out the actual shape with respect to the alkene, which is trigonal planar. Alright, so we have the two alkenes here, where I've expanded out the bonds and I draw the shape with respect to alkene carbon as trigonal planar, so that later we can see the arrangement of the groups in space. Then what we have to do next is we have to put in the groups. Now, if I look at this carbon on the left hand side, it is attached to a methyl group and a hydrogen. So this carbon will be attached to a methyl group and a hydrogen. I can put that in. I can put a CH3 here, and I put a hydrogen here. Actually, at the beginning, it doesn't really matter whether I put the methyl group on top or methyl group at the bottom, because later what we will do is we will draw the other isomer based on this isomer. So if the first isomer that you're drawing happen to be the cis isomer, then the next isomer that you would draw is the trans isomer, and vice versa. So in this case, I will draw the CH3 group on top, the hydrogen is at the bottom. Now this other carbon, as mentioned here, it is attached to a methyl group and a hydrogen. So same thing, I can put in the methyl group. In this case, I'll put it on top. Hydrogen, I put it at the bottom. As mentioned previously, it doesn't really matter where you put the groups, as long as you put the correct two groups. Now the next thing I want to do is I want to convert this isomer into the other isomer by flipping two of the groups that is attached to the same carbon. My practice, what I would do is I will fix the groups on the left hand side, I'll flip the groups on the right hand side. So let me show you what I mean. In order for me to convert one isomer to the other isomer, the carbon on this left hand side, CH3 is on top, so I will keep it on top, I leave it unchanged. This hydrogen is at the bottom, I'll put it at the bottom, I leave the carbon on the left hand side unchanged. But what I would do is I will swap the groups on the right hand side. So the isomer on the left hand side, the methyl group is on top. So for the isomer, what I have to do is I have to put the CH3 group at the bottom. So I'll flip this around. This CH3 group is on top. Now this CH3 group for the isomer is at the bottom. Then this hydrogen for the isomer on the left hand side is at the bottom. Then I'll have to draw it on top for the other isomer. Essentially what we are doing is we are switching the two groups that is attached to the same carbon. So this is how we convert one isomer to the other isomer for cis-trans isomerism. So now we have the two isomers. The next thing we want to do is we want to identify who is the cis isomer and who is the trans isomer. So each of these carbon inside this alkene is attached to 2 groups. And as mentioned, what we do is we focus on the bulky group or the big group. So this carbon is attached to 2 groups. The methyl group is bigger in terms of size. This carbon is attached to 2 different groups. The methyl group is bigger in terms of size. Similarly, for the other isomer, the methyl group would be the bulky group. The next thing we do is we look at whether the 2 groups are pointing at the same side or on opposite sides. This isomer on the left hand side, the bulky group and the double bond and the bulky group, actually it forms a C. So this will be the cis isomer. So we can name this as cis built to in because we already have the name here, built to in. So I need to add a tag in front to differentiate between this built to in and this built to in because they are named in the exact same way. They are called built to in. So we need to differentiate between both of these stereoisomers. We will need to add a special tag in front. This isomer will be the cis isomer. So this is a cis built to in. Now the partner, you notice the bulky group and the double bond and the other bulky group, actually it cuts across the compound. So therefore this will be the trans isomer. So the name for this guy will be a trans built to in. Now again, as mentioned previously, you notice in terms of the molecular formula and structural formula, these 2 guys are exactly the same. We need to show the actual bond angle with respect to the alkene, which is trigonal planar, in order for us to differentiate between cis built to in and trans built to in. Now the second type of stereoisomerism is optical isomerism. Now optical isomerism occurs for a chiral carbon. A chiral carbon is a saturated carbon or an sp3 hybridized carbon which is attached to 4 different groups. So we have an example here. This is butane 2-ol. Then you notice this carbon here, which is the second carbon, is attached to 4 different groups. It is attached to a methyl group, a hydrogen group, an ethyl group, and an OH group. And by convention, we will use an asterisk to annotate a chiral carbon. So we know that this carbon is chiral. It is attached to 4 different groups. Now if I have a chiral carbon, then this compound is asymmetrical. Then the mirror images of this compound are non-superimposable. That means we cannot overlap them exactly. So therefore they are different compounds. And these 2 different compounds, we call them optical isomers. Now let us try to draw out the 2 optical isomers. Now in order for us to show the optical isomers, we actually need to draw the actual 3D bonds with respect to the chiral carbon. So we have this here. This carbon is bonded to 4 different groups. These 2 bonds are lying along the plane. We will use a solid triangle to represent the bond that is pointing towards you, a dotted triangle to represent a bond that is pointing away from you, and this is the mirror plane. Then I'll mirror this chiral carbon. Then essentially what we do is we will just put in the 4 groups on one of these chiral carbon. Then we just mirror this accordingly on the opposite side. So let us try to do that. This carbon is bonded to a methyl group, an OH group, an ethyl group, and a hydrogen. Actually, the 4 groups, it doesn't really matter where we want to arrange them as long as we put the correct 4 groups. So let me try to put it in here. Maybe I put a methyl group here, CH3. The hydrogen is towards you. The OH group, maybe I point it up. And the ethyl group will be here, CH2, CH3. So this will be one of the optical isomers. Now in order for me to draw the mirror image, I just mirror this accordingly. The OH group is pointing up. So I'll draw this OH group pointing up. Keep in mind I need to show the CO bond. So when I draw the mirror image, I must also show the CO bond. Then the methyl group is pointing away from you for the left hand side. So its mirror image, the CH3 group should still be pointing away from you. Hydrogen is pointing towards you. So the mirror image, hydrogen would still be pointing towards you. Then for the ethyl group, CH2, CH3 is here. So CH2, CH3 will still be here. Now when we draw the mirror image, I can write the alkyl group as a CH3, CH2 group. There's no need for me to inverse this and write it as a H3C, H2C because it is understood that the hydrogen is attached to the carbon on the left hand side. So if I were to mirror a CH2CH3, I can write this as a CH3CH2 group. So the two mirror images are out. So these two mirror images are non-superimposable. So therefore there are different compounds. So we call these two compounds optical isomers or enantiomers. Now, one interesting difference in the physical property for optical isomers is the optical activity. In fact, this is the only difference in the physical property, which is the ability for the optical isomer to rotate plane polarized light. So if I have a compound which is optically active, so what it would do is when I shine plane polarized light through this compound, which is light that is vibrating in one direction, what it can do is it can rotate the light, and this light will come out rotated after it passes through this optically active sample. So what is interesting is for optical isomers, they will have the same magnitude of rotation. So when plane polarized light is shining through each of these optical isomers, the magnitude of rotation of the plane polarized light is the same, but in opposite directions. So for example, if let's say this optical isomer is capable of rotating plane polarized light 5 degrees clockwise, then the mirror image is like the evil twin brother for this optical isomer. Whatever he can do, I will do to the exact same extent. Is also 5 degrees, but I will do it in the opposite direction. I will do it counterclockwise. So this is an interesting physical property for optical isomers, and as mentioned, this is the only different physical property for enantiomers. Now I hope that this discussion involving Cis-Trans Isomerism and Optical Isomerism will let us better understand the different types of stereoisomers. If you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. Thanks for watching.